All right, in our last video here, we have two additional examples where we want to practice our understanding of rate conversions. In this first example, we are given an order. Our patient needs to receive fentanyl at a rate of 2.5 micrograms per minute as a continuous infusion. We're also given their weight, 165 pounds. We walk into the patient's room, checking them in the start of our shift. We see that the bag that's hanging is about to be set and start at the rate given on the screen here. So this pump is about to operate 150 mLs per hour. We need to determine whether or not this pump is set correctly for the order. A couple ways to approach this. One way is to just start with our order, which is 2.5 micrograms per minute, and to turn that into mLs per hour, minute, there we go. Turn that into mLs per hour to see, does that match the pump rate? The other way that we could potentially approach this is to start with the pump, which is 150 mLs per hour. Turn that into micrograms per minute to see, does that match the order? We should be comfortable doing either one of these because they're both rate conversions. They require us to go from micrograms and milliliters, converting between mass and volume, and time, going between minute and hour. And we have to use our bag, the bag that is hanging. And there's two ratios on here, and we looked at this bag earlier. We can use either one. I would encourage you to use the unit ratio of 10 micrograms per 1 ml, because if you're using the 1 ml, you're less likely to make a mistake in the multiplication. For the video here, I'm going to go over both ways. I'm going to start with just the first way. Let's turn those micrograms into milliliters, and we can do that using the bag, right? We have the strength of the medication, and then we can turn those minutes into hours. We should arrive at the same conclusion, whether it's accurate or it's not. So if I started my dimensional analysis with the order, and I wanted to turn the order into mLs per hour, I can turn micrograms to milliliters using 10 micrograms per ml. That looks good, right? Because there are 10 micrograms in each milliliter. And now I can turn minutes into hours using my understanding of time. So if I multiply all those numerators, I'll have 2.5 times 60. So 2.5 times 60 is 150. Divided by 10 is 15. So this patient, for this order, should be getting 15 milliliters per hour, not 150. So this is not correct. It looks like whoever set this or whoever calculated this was off by a power of 10, a factor of 10, which can happen. They may have forgot to divide. This would have been a massive problem, right? So we need to be able to check things before the pump starts. Let's double check that that's accurate. Now going the other direction, let's just double check. If they're getting 150 mLs per hour, how many micrograms per minute is that? I can go from mLs to micrograms using the bag, and I can go from hours to minutes. So it's just the reverse direction. mLs to micrograms. I know 1 ml has 10 micrograms. And then I want to divide by 60 because 1 hour is 60 minutes. And so I'm going to guess we get 25, but let's double check. So 150 times 10 divided by 60. Yes, this individual, according to the pump, if the pump started to operate, they would be getting 25 micrograms per minute, which is not equal to, this does not match the order. So that would have been a problem. Either one of these would be perfectly acceptable to show your work to justify the answer to this problem. Is this set correctly? It is not. The correct rate would be 15 mLs per hour. In our last problem, this one tends to give students some challenges. And the reason why is because they attempt to jump right into the calculation. We are given an order of Fexin. 700 milligrams needs to be given every 4 hours as a continuous infusion, and this needs to be infused in 30 minutes. Our bag has 500 mLs in it, and it contains 4 grams of the drug. We're using this tubing that has a drop factor of 20 drops per milliliter. I need to know what drop per minute rate is needed to complete this infusion. So at the end of my calculation, I need drops per minute. I think the trickiest part here is to kind of read through this problem and think about what to start with. In all the previous examples we've seen thus far, we were told the rate to start with. In the previous problem, we started with 2.5 micrograms per minute. Earlier, we started with 1 milliunit per minute, 4 milliequivalents per hour. We were given the rate to start with. In this problem, we have to think about what rate we're starting with. We have to create that. And specifically, if you want to try it, go ahead. In this problem, we need the patient to be given 700 milligrams. So I'm going to start with that as my numerator. Those 700 milligrams need to infuse over how much time? If you said 4 hours, then you made a mistake that many people do. 4 hours is how often we would be repeating this. We would repeat this every 4 hours. The infusion is actually running for 30 minutes. The infusion time is 30 minutes. The every 4 hours is how often we repeat it. Definitely important, but that's not used as our denominator. So my plan is to somehow get from milligrams all the way to drops. And I need to get from minutes to minutes. Okay, perfect. I'm good there. Denominator doesn't need to change. No time conversion needed. But how am I going to get from milligrams to drops? And I have to use the bag, and I have to use the tubing. If you want to pause the video here to write out what you think the plan would be, and this is probably, up to this point, the problem where a plan is going to be most important because there's a bunch of conversions. If you want to pause the video and try that. Our bag has 4 grams. We need to give milligrams. So I need to go from milligrams to grams so that I can turn those grams into milliliters, and then I can use the drop factor to turn that into drops. So I'm going to have to do these 3 conversions. And it's not that we couldn't have started the dimensional analysis and got to that point, but these problems aren't always, especially if we're not comfortable with them, we haven't seen them before, it's better to start with our plan and now begin the dimensional analysis. So we're starting with 700 milligrams over 30 minutes. And now I'm following through with exactly what I said I was going to do. I already have minutes, so I'm going to circle that. I want to turn those milligrams into grams. 1 gram is 1,000 milligrams. I now want to turn those grams into milliliters. There's 4 grams of the drug in 500 mLs. That bag is 500 milliliters. And I'm not quite done because I'm going to be using the tubing that will allow me to convert those volumes. There are 20 drops in 1 milliliter. So let's put all of this into our calculator. So I'm going to have 700 times 500 times 20. And I'm going to divide by 30 times 1,000 times 4. I got 58.3 repeating, and this is drops per minute. And since we are going to be counting these drops, we need to round to the nearest whole number. So this would be 58 drops per minute. There's lots of ways that you could have done this without showing the dimensional analysis that I have here. Some students like to look at this problem and say, well, I need milligrams. In order for the bag to match the order, I would love if this bag was already in milligrams. So they'll look at this and say, well, I know I need milligrams. 4 grams times 1,000. This bag has 4,000 milligrams of the drug. If you are comfortable doing that, that makes sense to you, by all means, feel free to do that. Another way to think about this problem is to just convert the order into grams. So some like to think, well, if I know it's 700 milligrams, that's equivalent to 0.7 grams. You're welcome to do that as well. The point here is to think about the conversions that are needed before starting your dimensional analysis.